Hello, and welcome to lecture number 2 of our mini course on the dynamics of circle maps. You saw in lecture 1 given by my friend Pablo, Guarino, basic facts about rotations, and he also explained to you the basic topological dynamics of homeomorphisms of the circle. So by now you're familiar with all the terminology, and he also spoke about rotation numbers and the continued fraction development of rotation numbers. He did a little bit of continued fraction theory for you in part 2 of his lecture. So in this second lecture, I want to present you an overview of the theory of circle diffeomorphisms, okay? The lecture has been divided into 2 parts, and this is part 1. Part 1 is about the topological classification and some ergodic properties of such diffeomorphisms. Part 2 deals with the smooth rigidity of such maps, okay, or in other words, the smooth classification of such diffeos. So in part 1, we will start by discussing fundamental theorem due to Danjois. We will also discuss a little bit about the so-called Danjois counterexamples. So these are diffeomorphisms having exceptional minimal sets. Then we go back to maps which are minimal, and we will discuss certain ergodic properties of these maps. So in particular, the fact that they're always ergodic with respect to Lebesgue measure. And we will also discuss the Lyapunov exponents of such maps. Okay? In part 2, we will look at a fundamental theorem due to Arnold, which is a local analytic conjugacy theorem for such diffeomorphisms when they are analytic. And then we will discuss one-parameter families of such maps and present some counterexamples also due to Arnold to analytic linearizability of such maps. And finally, we will give you a kind of a glimpse into the so-called Hermann-Yocos theory for smooth diffeos. Okay, so this is the start of part 1. So let's discuss briefly what's called Danjois theory. So Danjois investigated the problem of when a circle diffeomorphism is topologically conjugate to a rotation, okay? So in this lecture, and in practically all lectures in this course, we will primarily be interested in maps which have no periodic orbits, because when a circle homeomorphism or diffeomorphism has a periodic orbit, then it's easy to reduce the study of its dynamics to the study of the dynamics of an interval homeomorphism. And the dynamics of interval homeos is rather trivial. So we're not going to worry about that. Okay. So we are interested in diffeomorphisms in this lecture, and the diffeomorphisms will be, unless explicitly stated or otherwise, they will be diffeos without any periodic orbits. So the main result proved by Danjois in 1932 is this theorem. It states that if you have a diffeomorphism of the circle, which has a little bit more smoothness than being just C1, if it's C1 plus bounded variation, and it has irrational rotation number alpha, then this diffeo is actually topologically conjugate to the rotation R alpha. So here, to say that f is C1 plus bounded variation means that the logarithm of its derivative of log of df is a function of bounded variation on the circle, okay? There are other versions of Danjois' theorem, and in fact, if you look at, for instance, Hermann's thesis from the late 70s, you will find, sharper versions. But there is a new version from the last 20-something years which is due to Hu and Sullivan, which instead of assuming that the logarithm of the derivative is a function of bounded variation, it assumes that it is what we call a Zygmund function. So it's in the Zygmund class. So it satisfies this condition that you see here at the bottom, phi of x plus h plus phi of x minus h minus 2 times phi of x is big O of h, okay? So a function with this property is called Zygmund. And the Zygmund class and the bounded variation class, they don't have much to do with each other. They have a large intersection, but neither class is contained in the other. So these are really different versions of Danjois' theorem. The conclusion is the same, that you have a topological conjugacy between F and the rotation. So I want to give you an idea of how this theorem is proved. The fundamental tool to prove this theorem is something which is now called the Danjois-Koxma inequality. So what is this inequality all about? Well, it's actually for homeomorphisms. So the hypothesis here is very weak. You have a homeomorphism with rational rotation number, and you know that such homeos are uniquely ergodic. So there is a unique Borel probability measure which is invariant under the map F. So you take this measure, mu, and now for every good rational approximation to the rotation number, by good approximation, I mean the rational number P over Q is at a distance less than 1 over Q squared from alpha. Then if you take any observable, any function of bounded variation on the phase space, which is the circle, then if you look at its time averages, okay, up to time q, where q is this denominator of this rational number that you've picked, then the time average of phi up to time q differs from the space average, which is the integral of phi with respect to the invariant measure, by less than a constant divided by q. And this constant is just the variation of phi, okay? Now, and the inequality is really taking the supremum over all x, you still have this inequality, okay? Now, what is this saying? We know that since f is uniquely ergodic, well, it is ergodic for the measure mu, so we know from Birkhoff's ergodic theorem that the time averages converge to the space average, okay? The convergence is for almost every point with respect to the measure mu, but here, because phi is continuous, and because we have unique ergodicity, this convergence is actually at every point, okay? So what is Danjois-Koxma saying? Danjois-Koxma is saying that not only you have this convergence, but along a subsequence of times, you can actually bound the error term, how much the time average differs from the space average along the subsequence of times q given by the best rational approximations or good rational approximations to alpha, okay? I will not go into the proof of this inequality, but I will show you now how to use this inequality to prove Danjois' theorem. So the idea here is you look at phi equal to the logarithm of the derivative of f. This is a function of bounded variation by hypothesis. And you look at the sequence Qn of closest return times of f. This was defined in lecture number 1. The Qn's are precisely the denominators of the best rational approximations to alpha. So in fact, if you express alpha as a continued fraction and you truncate the continued fraction at the nth step, you get a rational number called Pn over Qn, right? And these are the Qn's that I'm talking about. So this sequence Qn, what's important about it is that it's going to infinity as n goes to infinity. So you apply the Danjois-Koxma inequality to this function phi, which is the logarithm of df, and for the times q equal to these Qn's that I just defined. And the inequality is telling you what you see here on the screen. You know this inequality labeled 1 here. So the time average of the logarithm of the derivative of f up to time Qn differs from the space average, from the integral of log df with respect to the invariant measure, by less than the variation of the logarithm divided by qn. Okay, and this is at all points. Now, let's apply this inequality to a special point. You can take a point for each n, right? So you're looking at this time average up to time qn. So for each n, you can find a point where the derivative of the iterate fqn at that point is equal to 1. This is just by the mean value theorem, right? I mean, fqn is a diffeomorphism of the circle. So its derivative cannot be greater than 1 at all points, and it cannot be less than 1 at all points. Otherwise, the circle would be increasing or decreasing in size, which is not the case, right? So you know that there is a point where the derivative is 1. So the logarithm of the derivative of fqn at that point must be 0. And so the sum that appears on the left-hand side of this inequality 1, the sum here is 0. So if you do that, you deduce that the integral of the log of the derivative of f is less than v over qn for all n. And since the qn's are going to infinity, this means then that the integral must be 0. So now you know that the integral is vanishes. So you can go back to this inequality, and you set the integral equal to 0. And remember that the sum of the logarithm of the f composed with fj from j going to 0 to qn minus 1 is precisely the logarithm of df of qn, as you see here at the bottom. So if you plug this information in, you deduce that the logarithm of the df of qn at any point x on the circle is in absolute value less than v, which is a constant. So this means that df of qn is bounded above and below by these positive constants, e to the v and e to the minus v, okay? So what is this saying? This is saying in particular that the sequence of iterates fqn is an equicontinuous sequence. And as you saw in lecture 1, Pablo mentioned this, this is a criterion for a map to be, for a homeomorphism of the circle to be topologically conjugate to a rotation. The fact that there is a subsequence of times along which the iterates of f form an equicontinuous family rules out the existence of wandering intervals, and therefore f must be minimal, so it must be topologically conjugate to the rotation R alpha. So that's the proof of Danjois' theorem using Danjois-Koxma, okay? Now, what happens if you have less smoothness than C1 plus bounded variation? So in this situation, you can have, Danjois showed that you can actually have non-minimal maps. So you can have exceptional minimal sets for these maps, okay? We saw in lecture 1 that the non-wandering set of a circle homeomorphism without periodic points can be either the whole circle, okay? So that's the case when f is minimal, or it can be a Cantor set. But in any case, in any case, f acts on the non-wandering set in a minimal way. So the action is minimal, and it's even uniquely ergodic. Okay, we saw this in lecture number 1. And when the non-wandering set is not the whole circle, in other words, when it's a Cantor set, then we say that we have an exceptional minimal set. We have a map with an exceptional minimal set. Pablo also mentioned in lecture number 1 that every Cantor set on the circle can be realized as the minimal set of a homeomorphism. And you can even choose the rotation number to be any irrational that you like. So what happens for diffeomorphisms? Well, the situation is a bit more subtle here. It's considerably more subtle, in fact, if you require f to be a diffeomorphism, okay? There are, in fact, even still open problems regarding this situation. I should mention that the first example of a C1 diffeomorphism of the circle having an exceptional minimal set, leaving in other words, leaving invariant Cantor set on the circle, was constructed by Boll much earlier, in 1916. So this is 16 years before Danjois constructed these examples. But Danjois' analysis is, of course, much more complete. He went further and he actually showed that you could construct these examples to be a little bit better than C1. You could actually have these examples to have the property that the logarithm of the derivative of the map is Holder continuous of some exponent. Later, this was sharpened by other authors like Herman and Katznelson in the 70s. And in particular, they showed that you can build these examples in such a way that they are almost Lipschitz, okay? They can be made C1 plus epsilon for every epsilon between 0 and 1, and without any restriction on the rotation number, okay? So combining these, we can state Danjois' counterexamples as a theorem in the following way. So for each L between 0 and 1, strictly less than 1, each positive beta and each rotation number between 0 and 1, irrational, okay? There exists a C1 diffeomorphism with the following properties. Well, first of all, F has rotation number equal to alpha. The second property is that the non-wandering set is a Cantor set, so we have an exceptional minimal set. And the Lebesgue measure is equal to this L that was given to you. And finally, the logarithm of the derivative is a function which has this strange modulus of continuity W sub beta equal to T times the logarithm of 1 over T raised to the power 1 plus beta, okay, where beta is this positive number that was given. And with this property, you actually deduce, it's an easy exercise to show that this modulus of continuity is stronger than Holder for every Holder exponent between 0 and 1. So these examples are actually Holder continuous, delta Holder continuous for every delta between 0 and 1, okay? So I'll give you an idea, just a very simple, quick idea of the proof. But first, let's look at the topological construction. The topological construction has already been described in lecture number 1. What you can do here, I'm going to structure the description in a different way. So you can, first you choose a bi-infinite sequence of pairwise disjoint intervals on the circle in such a way that they are ordered on the circle in the same way as the orbit of a rotation with rotation number alpha, okay? And in such a way that if you look at the complement of the union of these intervals, what you get is a Cantor set. It's a perfect and nowhere dense closed set on the circle, so compact. So it's a Cantor set, okay? Well, how do you deploy the intervals on the circle so as to satisfy this condition, these conditions, is a little bit tricky. But if you look into the book, our book for the series of lectures, you will see the careful construction of these intervals and everything else. Then you define a homeomorphism in such a way that this homeomorphism maps each interval I sub n into the next one in the sequence for all n in Z, okay? Homeomorphically, of course. And then just by continuity, you actually get a homeomorphism of the whole circle. And it's not difficult to see that it will have rotation number alpha by construction. In fact, you can even tell what the semi-conjugacy to the rotation is. So, for instance, you look at an orbit of the rotation R alpha on the circle. So let's say alpha n is the iterates of 0 under R alpha. Okay, 0 here is because I always identify the circle, the unit circle, as R mod Z. Okay, and 0 here represents the equivalence class of 0 under this quotient R mod 0, R mod Z. Okay, so you look at this orbit, and then you define a monotone function of the circle to itself. What you do is you you look at, for each alpha n, you look at the preimage of this guy, you specify that the preimage of this guy is equal to the interval I sub n. Okay, so the I sub n's become like plateaus for the map H, and because of the order structure, there is like a unique extension, continuous extension of H to the whole circle, and so you get a continuous monotone map of the circle, and that's a semi-conjugacy between F and the rotation, as you can see in the figure that I'm going to show you in a moment. But the upshot of this is that the non-wandering set becomes this Cantor set K that was constructed. And this Cantor set, of course, has Lebesgue measure equal to 1 minus the sum of the lengths of all these pairwise disjoint intervals I sub n. Okay? So you can specify the measure of the minimal set. You can specify the rotation number. And what you haven't done yet is to make the map into a diffeomorphism. So can this recipe here be applied to produce a diffeomorphism of the circle? So here's the picture first illustrating the fact that I just mentioned, that F is semi-conjugate to the rotation R alpha, okay? So the I sub n's are plateaus for the semi-conjugacy. Now, if you have a diffeomorphism, then you have a problem. The intervals have to be very carefully chosen, and particularly the lengths of these intervals have to be very carefully chosen, because you want a diffeomorphism now. And you have a certain liberty, you have a certain freedom to define the map on the gaps of the Cantor set on these intervals I sub n, but not much freedom, okay? So one convenient way of doing the construction is to define these diffeomorphisms in such a way that the derivative is piecewise affine, okay? Once again, all the details of this construction can be found in our book, in chapter 4 of our book. Now, as it happens, you need two conditions to be satisfied for the construction to work. The first is that as you let n go to infinity in the positive or negative directions, the ratio between successive intervals in this sequence, in this bi-infinite sequence, has to go to 1 as n goes to infinity, okay? And the second condition is that they, in any case, they cannot differ too much from 1, you know? They have to stay, you know, close to 1 in some sense, for all values of n. Okay, so a good choice of lengths turns out to be given by this funny expression that you see here. So you can take the intervals to be such that their lengths are given by a constant divided by essentially n plus 1. So it's essentially n times log n raised to the power 1 plus beta. The reason why we add 1 to n here and add 2 to n inside the logarithm is of course to avoid 0 in the denominator, okay? But it's essentially a constant divided by n times log n raised to this power 1 plus beta, which is slightly better than 1, right? The constant is chosen so that the intervals, you know, when you add up the lengths of these intervals, you get precisely this L that was given to you in the statement, okay? And there is a mistake here. It's written that L is less than or equal to 1, but, well, no, that's actually correct. L is less than or equal to 1, okay? And 1 minus L is then going to be the desired Lebesgue measure of the Cantor set, okay? So the choice is made of the lengths, but of course you have to deploy the intervals in the correct way on the circle, and for this you have to use the order of the rotation by alpha. So the actual deployment of the intervals on the circle is not completely clear. So once again, there are details here that are being swept under the rug, and you should look in chapter 4 for a description. But now it turns out that with these choices, you see, because the ratios of the lengths of I sub n plus 1 and I sub n, because these ratios are going to 1, what you get in the limit is that your diffeomorphism has derivative 1 at the non-wandering set, okay? And it's also not difficult to prove. Once again, look at chapter 4 for the proof that the logarithm of the derivative has precisely this modulus of continuity that was given in the statement. So it satisfies this inequality label 3 here in the slide, okay? And this modulus of continuity, as I mentioned before, it's an exercise. It implies that phi is actually a delta holder continuous for every delta between 0 and 1. So this is the basic, outline of the construction. But of course, there are many details there. But this raises also the question, which Cantor sets can be made into exceptional minimal sets for C1 diffeomorphisms of the circle, okay? This question is still, in some sense, open, okay? A full classification of all Cantor sets that appear as exceptional minimal sets is not really known. And in fact, there are some negative results. So, you can ask this question, is every Cantor set, just like for homeomorphisms, you know that every Cantor set is an exceptional minimal set for a homeomorphism. So you can ask this question, is every Cantor set an exceptional minimal set for some diffeomorphism of class C1? And the answer is no, okay? For example, if you look at the standard middle thirds Cantor set and you wrap it up on the circle, right? You remember that the circle for me is R mod Z. So you take the standard Cantor set in the interval 0, 1, and you just take the quotient of R by Z. You have the standard middle thirds Cantor set placed on the circle now. This is not a C1 minimal set. And this follows from a criterion that was first proved by Dusa McDuff in 1981. And to state her result, I need a definition, okay? So if you have a Cantor set on the circle, you can look at the complement of this Cantor set. So you have all the gaps, the connected components of the complement of this Cantor set. And you can define something called the spectrum of this Cantor set, which is the set of all lengths that appear in the gaps. Okay, so you look at all gaps, and you look at all possible lengths. And since this is a countable collection of intervals, there will be a countable collection of lengths, and you organize them in descending order, okay? So that's the spectrum. The spectrum is denoted sigma of k, okay? So it's a collection of lengths of intervals, which is organized in descending order, okay? Strictly descending, okay? Okay, so that's the spectrum. And of course, because the sum of the lengths of all the intervals on the circle is less than or equal to 1, so are the lengths appearing in the spectrum, right? So the theorem by Dusa McDuff is the following. If you have a C1 diffeomorphism that has no periodic points and which has an exceptional minimal set, so the non-wandering set of F is not the whole circle, then if you look at its the spectrum of this Cantor set, then the sequence of ratios of successive lengths, Ln, so Ln divided by Ln plus 1, the sequence is bounded, okay, and one has a limit point. Okay, of course, the sequence is the way it's written. The sequence is a sequence of numbers always greater than 1. So what this is saying is equivalent to saying that the infemen over all n of Ln divided by Ln plus 1 is equal to 1. Okay. All right. So this condition, the problem with this condition is that it's definitely it's a geometric condition on the Cantor set, but it's definitely non-dynamical. Okay, there's nothing dynamical about it. So it's not difficult to show. It's actually can be left as an exercise for you to show that the sequence of ratios is actually bounded. It's not difficult. It's easy. Okay. The problem is showing that 1 is a limit point. Now this, of course, immediately rules out the middle third Cantor set as a C1, as a possible C1 minimal set, because in this case the ratios are always equal to 3, right? I mean, in the first generation of the construction of the middle thirds, you take the middle third, which has length 1/3. Then you're left with 2 intervals with length 1/3. So you take the middle thirds of those. Those have lengths 1/9, right? And then at the next stage, 1/27, and at the next stage, 1/81, and so forth. So the ratios of the different lengths that appear, are 1/3, 1/9, 1/27, and so on. And the ratio between 2 consecutive ones is always equal to 3. Okay. So this result by MacDuff was later extended by Alec Norton and also by Aldo Portela. These results, they are extensions in the sense they rule out more Cantor sets as possible C1 minimal sets. Okay. So that's the situation. So not all Cantor sets appear as C1 minimal sets, but you can also investigate the problem from the point of view of other geometric properties, such as the Hausdorff dimension. So I would like to mention to you here a more recent result. So if you're looking at Danjoy examples that have 0 Lebesgue measure, it makes sense to ask, well, what is the Hausdorff dimension of this minimal set? Okay, it has 0 Lebesgue measure. So what is the Hausdorff dimension? So what are the possible values for the Hausdorff dimension? And it turns out there is a slightly surprising answer here, is that the answer depends on the nature of the rotation number of F. Okay. More precisely, it depends on the so-called Diophantine character of the rotation number. So let me remind you of what Diophantine means. This was explained by Pablo in his first lecture, but here I'm going to state it in a slightly different way. So we say that an irrational number alpha is of Diophantine class given by tau if you have this inequality, okay? Or in other words, if the following inequality has infinitely many solutions, if eta is less than tau, and only finitely many solutions is if eta is greater than tau. So what is the inequality? The inequality is just saying that the distance between alpha and the rational p over q is smaller than 1 over q to the power 1 plus eta. Okay? So this is what it means to say that alpha belongs to the Diophantine class tau. Okay? So it's well approximated by rationals in this sense, in the sense of this inequality. Okay? So the theorem stated by proved by Breiner and Schmeling, Jürgen Schmeling, is the following. So suppose you have a number delta between 0 and 1, and you take an irrational number between 0 and 1, which is of Diophantine class tau greater than 0. Okay, then if F is a C1 plus delta diffeomorphism, so if it's a diffeomorphism with the property that the logarithm of the derivative of F is Holder continuous of exponent delta, okay, and you know that F has this irrational rotation number alpha and an exceptional minimal set, then the Hausdorff dimension of this exceptional minimal set, this Cantor set, must be greater than or equal to delta divided by tau. Okay. Well, it turns out that this lower bound is sharp. And interestingly enough, Krah and Schmeling also, in showing that it's sharp, they actually showed that the lower bound is achieved by the classical Danjois example. So these are examples that are constructed using this sequence of gaps, of lengths of gaps given by this expression that you see here. So the length of I sub n is a constant divided by essentially a power of n, which is 1 over delta. Okay, once again, we take n, we take the absolute value because n here is an integer, and we add 1 to avoid 0 to not have a 0 in the denominator, right? But essentially what this is saying is that you can choose the length so that the length is equal to a constant divided by n to the power 1 over delta. And of course, the constant has to be chosen so that the sum of the lengths is equal to 1 because you want the Cantor set to have measure 0, okay? So if this happens, then you have that the Hausdorff dimension is exactly equal to delta over tau. They also, in the same paper, Krah and Schmeling also provided the lower bound for the so-called box dimension, which is a weaker invariant than Hausdorff dimension, okay? I'm not going to talk about that, but in doing so, they generalized a previous work due to Alec Norton. Okay, so now that we've discussed these Danjois examples from these points of view, so let's go back to the situation where we have a map which is C1 plus bounded variation. We have a diffeomorphism which is C1 plus bounded variation and no periodic orbits. So we know that in this case it's minimal, and it turns out that these maps are actually ergodic with respect to Lebesgue measures. So what that means is the following. So it's a general thing is that you can talk about ergodicity of a map with respect to a measure in phase space, even if the measure is not invariant under the map. Okay, so even if the map is not measure preserving, you can still talk about ergodicity in the following sense. So you have a measure space and you have a measurable map. Then you can say that this map is ergodic with respect to the measure if every invariant set under this map, okay, either has measure 0 or its complement has measure 0. Okay, so that's a notion. We say that phi is ergodic with respect to the measure mu, even though the measure mu is not invariant. Okay. Now it's not necessary to even assume that that mu is a finite measure. It could be a sigma finite measure, no problem. Okay, the notion still makes sense. But in any case, for us, this theorem is what's true about it is that if you have a C1 diffeomorphism of the circle which has no periodic points, and if the logarithm of its derivative is a function of bounded variation of the circle, then f is ergodic with respect to Lebesgue measure, okay, which is not invariant unless f is a rotation. Okay. Now, I will not prove this theorem. This theorem is also proven and this is actually proven in chapter 3 of our book. Okay, so I'll leave you with the task of going to the book and reading the proof. But I will give you some idea of the proof of another result, which is quite natural, which says that these diffeomorphisms of the circle, they always have 0 Lyapunov exponents. So let me first define what Lyapunov exponent means, right? So for a one-dimensional map, the Lyapunov exponent is essentially a number that measures the exponential growth rate of the sequence of derivatives along an orbit. Okay, so the formal definition is this one. So I'm denoting it, the Lyapunov exponent at a point x to be this chi sub f of x, which is just the limit of 1 over n times the logarithm of the absolute value of the derivative of fn calculated at x, provided the limit exists. Well, this sequence of derivatives is actually a multiplicative sequence. So when you take the logarithm, it's actually an additive sequence. So the limit is, you can say the limit exists, okay? The only trouble would be if you had some critical point here, because then you would have log of 0, which is definitely not possible. But we're dealing with diffeomorphisms here in any case, okay? So when the forward orbit of f hits a critical point, then we just set chi sub f of x to be equal to minus infinity, because in that case, you're going to get log of 0, which you would think of it as being minus infinity. Now, we're just interested in the diffeomorphism case anyway, so this is not going to happen. But, you know, when the Lyapunov exponent is non-zero, this points to a certain hyperbolicity of your map, okay? So, in fact, asymptotic hyperbolicity. So you have an asymptotic contraction if the Lyapunov exponent is negative, and asymptotic expansion if it's positive, okay? So since circle diffeomorphism, it's quite clear now, you know, that if it's conjugate to a rotation, then there is no hyperbolic behavior at all, right? There's no asymptotic contraction, there's no asymptotic expansion. So you expect the Lyapunov exponents to be 0. And this is precisely the content of the following theorem. So if you exclude periodic points, of course, it's important to exclude periodic points here. If your map has a periodic point and it has like an attracting periodic point, like for instance, if you have a diffeomorphism of the circle, which is a Morse-Mail diffeomorphism, as mentioned by Pablo in his first lecture, then you have like a contracting periodic points, and you also have expanding periodic points. So if you look at the dfn of x for those points, you'll see either a huge contraction or a huge expansion asymptotically. So you have Lyapunov exponents which are non-zero in that case. So I'm excluding maps with periodic points. So it's intuitively clear, sorry, that for these cases, the Lyapunov exponents should be 0. And this is precisely the contents of this theorem. So if you have an orientation-preserving C1 diffeomorphism of the circle with a rational rotation number, then it actually must have Lyapunov exponent 0 at all points. Now, this is just, in some sense, this has an easy proof, and the proof is the following. So you take the function log df again, and by hypothesis, this is continuous because the map is C1. And because f is uniquely ergodic, which is something we know already, then the sequence of continuous functions, which are the Birkhoff averages of phi along the orbits of f, right? The sequence of continuous functions, the sequence converges uniformly to the space average, okay, to a constant, and the constant is the space average of log of the f, okay? So it's the integral of phi with respect to the measure mu. Okay, but on the other hand, you know from the chain rule that the sum that appears in this Birkhoff average is just the logarithm of the derivative of fn, okay? So what this is saying is that the sequence 1 over n log of the fn converges to this constant. And the convergence is uniform in S1, okay, on the circle. Okay, so suppose the constant is positive. This constant L is positive. So what does that mean? That means, because you have this uniform convergence, this means that after some time, the 1 over n of log dfn must be positive at all points in the circle. So this actually means that dfn of x is greater than 1 at all points on the circle, okay, for all n sufficiently large. But this is impossible, right? Because fn is a diffeomorphism of S1 onto itself, and we know that there are always points where the derivative is 1, okay? And if there are points where the derivative is greater than 1, there must be points where the derivative is less than 1. Otherwise, the circle is either increasing, otherwise the circle would be increasing in size, which is not the case, okay? So this rules out L positive, and the same argument rules out L negative, right? Because now you would have dfn less than 1 for all x, okay? So L must be equal to 0. So the integral of the logarithm of df is 0, and since it's the limit of the Birkhoff averages everywhere, this limit must be 0 also everywhere. So this proves the theorem, okay? And this closes part 1 of my lecture. Stay tuned for part 2, okay? Hello, and welcome to part 2 of the second lecture of our mini course on the dynamics of circle mappings. In the first part, I discussed the topological theory of diffeomorphisms, the topological classification of diffeomorphisms. In this lecture, in the second part of the lecture, I want to discuss the smooth classification of such diffeomorphisms, okay? I should start by apologizing because in the first lecture, I kept referring to chapter 4 for the material of the first part of the lecture, but that should have been chapter 3, okay? I was constantly saying, see chapter 4, but it was actually chapter 3 that I should have told you. The reference for this part that I'm going to talk about today is chapter 4, okay? So, the topic here is the smooth rigidity of diffeomorphisms of the circle, okay, of smooth diffeomorphisms. The word smooth here is a little bit, I'm using it a little bit vaguely. It will mean different things in different contexts. It might mean ck for some positive integer k, or it might be C infinity or even a real analytic, okay? So as we saw in the first part of the lecture, if you have a reasonably smooth diffeomorphism of the circle, which is has no periodic points, then we know it's minimal, so it's topologically conjugate to the corresponding rotation, and therefore topologically the orbit structure of this diffeo is completely indistinguishable from the orbit structure of the rigid rotation with that same rotation number, right? But the question arises as to what can we say about the geometric orbit structure, okay? So I'm being vague here about what I mean by geometric orbit structure. I'll say just a couple of words in a moment. But intuitively, what it means is that you look at the way the points deploy themselves on the circle up to a certain time, the points in the orbit of a given point, and you compare that with the corresponding orbit of the rotation under the topological conjugacy. And you ask whether the distances somehow are more or less the same, or at least asymptotically the same, okay? This is a question which is quite subtle, and the answer depends on the arithmetic nature of the rotation number. So this means that it depends on how well or how badly this irrational rotation number is approximated by rationals, okay? I will have more to say about that in a moment. But the intuitive meaning of geometric structure is as follows. You take a point on the circle and you iterate up to a certain time n. So now you have this finitely many points on the circle which are part of an orbit. And then you look at ratios of lengths between consecutive points on this orbit, and you record these ratios of lengths. And then as you increase n, you try to compare this with what happens with the rotation. And if it's asymptotically the same, if the ratios kind of become asymptotically the same, then you say that the geometric structure is the same, okay? So, and if we only care about these distances and these ratios of distances for smaller and smaller scales, then we are actually talking about the asymptotic geometric structure of the map, okay? Now, if you, for example, if you have a C1 diffeomorphism, right, and suppose you know it's already a conjugate to rotation, and that the conjugacy is a C1 diffeomorphism, okay? Then if you look at it at smaller and smaller scales, it becomes closer and closer to, you know, the map age, the conjugacy age becomes closer and closer to becoming affine, to being affine. So this allows us to rephrase the question that we posed before in the following way. So if a C1 circle diffeomorphism is topologically conjugate to an irrational rotation, when is it a C1 conjugate? Okay, when is the conjugacy C1? Okay, this problem can actually be generalized. So this is part of a more general problem, which can be stated as follows. You know, find necessary and sufficient conditions for a circle diffeo, which you know is topologically conjugate to an irrational rotation, to be smoothly conjugate to that rotation, or in other words, to be CS conjugate to that rotation, where S is as large as possible. Of course, it has to be less than the degree of smoothness of the map itself, right? Now, this is the fundamental problem, and it has been really, you know, truly investigated by, especially by these three mathematicians, Arnold, Hermann, and Yocos. But there are inputs from several other people, and including Katz-Nelson, Ornstein, and so on. And my goal in this lecture is to tell you a little bit about this story. I mean, tell you what the results are. So what I'm going to do is, by the end of this lecture, I'm just going to give you some statements, okay? Before that, we will try to do some math and try to, you know, at least give us a flavor of some proofs of something, okay? The first thing I want to do is tell you about some invariants that were introduced by Michel Hermann in the late 70s. They give you a necessary and sufficient condition for a circle diffeomorphism of class CR to be CR conjugate to the corresponding rigid rotation, okay, with the same rotation number. So Hermann defined his invariance in the following way. You take your map, which you know is CR. You look at its iterates, Fn, positive and negative. You're going, you know, backwards and forwards. And you look at the derivatives of these iterates and look at the CR minus 1 norm of these derivatives and take the supremum over all possible iterates. So that gives you an extended positive number. It could be infinity in principle. And okay, so what do I mean? First of all, what do I mean by CR norm, right? So the CR minus 1 norm. So if you have a CK function, I'm writing that the CK norm of this function is just the sum of the C0 norms of all derivatives of phi up to k, okay? So Hermann's invariant is an invariant in the following sense. If you have a map, which is CR, you have a CR diffeo, and you have another CR diffeo H, and you conjugate F by H, then the invariant, this number H sub R of F, it will be finite if and only if it is also finite for the conjugated map, okay? So it's invariant in this sense. These numbers are either both finite or they're both infinite, okay? Now, the proof of this, of the fact that it is an invariant for R equals to 1 is very easy. It's just you know, very easy use of the chain rule, because if the map F is, you know, if you conjugate the map F by age, then the iterates of this conjugate map are just given by age, composed with f to the n, where n is the power, composed with age inverse, okay? So it follows from the chain rule that, h1 of f is finite if and only if h1 of h composed with f composed with h1 is finite. And by the way, there is a little misprint here. In this equation here, I should have written that hr of h composed with f composed with h inverse is finite if and only if h sub r of f is also finite. Okay, it's written 1 there in the equation, in the equivalence. So sorry about that mistake. So the proof for r equals 1 is immediate from the chain rule. For r greater than 1, it's a little bit more technical. It involves knowing something about the higher derivatives of a composition of functions. And there is a formula for that. It's called the Fadi-Bruno formula, okay? I will not go into that, but I will show you what Hermann's criterion is. So Hermann says, if you have a CR diffeomorphism, and if you calculate Hermann's invariant, h sub r of f, and you get a finite number, then f is CR conjugate to the rigid rotation with the same rotation number, okay? And conversely, and here, there is no assumption on whether the rotation number is rational or irrational, okay? The proof doesn't feel that, so it works for rational rotation numbers as well. Of course, a map will only be, conjugate to a rational rotation if it's actually a rational rotation, right? Well, sort of. So we will only prove this criterion for r equals 1, okay? For r equals 1, it turns out that this is a consequence of a very nice theorem that it's sort of old. It's from the 1940s or 50s, which is the so-called Gottschalk-Hedlund theorem. So this theorem is for homeomorphisms of a compact metric space. And you assume that all the orbits are dense, okay? So this homeomorphism is a transitive homeomorphism. And you look at a certain observable on your phase space, a certain function from x to r, which is continuous. Then the following two statements are equivalent. The first one says that phi is what we call a dynamical co-boundary. So phi can be written as the difference psi composed with f minus psi for some continuous function psi. So that's one assertion. The second assertion is that there exists a point such that if you look at the sum of this observable along the orbit of this point up to time n, and you take the sup over all n, this number is finite. So these two assertions are equivalent. That's the contents of the Gottschalk-Hedlund theorem, okay? And Hermann's criterion for r equals 1 follows from this, and I will show you how it follows, okay? So let me just repeat Hermann's criterion for r equals 1. It's just saying that a C1 diffeo of the circle is C1 conjugate to a rotation if and only if this first invariant, Hermann's first invariant at f is finite. So let's give the proof. So in one direction, so the real difficult direction or non-trivial direction is this one. You assume that the invariant is finite, and you want to show that f is a C1 conjugate to rotation, okay? Now, by the chain rule, you can write that the log of dfn for every iterate n, positive, say, log of dfn is the sum from j equals 0 to n minus 1 of log df calculated at the iterates of f to the j. And therefore, if you look at this, what this says, if you look at the function log df, this function satisfies the second condition in the Gottschalk-Hedlund theorem, right? So, which I remind you says that the sup of these sums is finite, okay? Why is that? Well, it's immediate that it satisfies condition B, so therefore it satisfies condition A as well. Okay, so you can write the logarithm of the derivative of f as a co-boundary. It is a co-boundary, so you can write it as the difference psi minus psi composed with f for some continuous function defined on the circle. And of course, if you add a constant to psi, nothing changes, right? Nothing changes. So you can choose the constant in such a way that this integral that you see here, the integral of the exponential of psi on the whole circle, is equal to 1, okay? Now, if you have that, then you can define a map from the circle to itself by this formula. H of x is equal to the integral from x0 to x of the exponential of psi. Now, of course, when I do that, what I'm doing is I'm, as usual, identifying the unit circle with r mod z, okay? So I'm writing the circle additively, and all calculations, in fact, that are going to be made here, they are modulo 1. You should take that into account. You should keep that in mind, okay? All right, so first of all, this is going to be a C1 diffeo because psi is continuous. One thing you should check is that H is well defined. So you see, if you start with, if you go and try to calculate H of x0 plus 1, well, x0 plus 1 mod 1, you're back to x0, right? So it better be true that the integral from x0 to x0 plus 1, okay, gives you the same thing as has H of x0, right? And that's just because of this condition, this choice of constant that makes the exponential of psi, the integral of that, to be equal to 1. Okay, so H is well defined, and since psi is continuous, H is a diffeomorphism. Okay, it has degree 1, first of all. And why is it a diffeomorphism? Well, if it has degree 1, the only thing you have to check is that it's a local diffeomorphism. But obviously, H is differentiable by the fundamental theorem of calculus, of course, and H prime of x is equal to the exponential of psi of x, which is always positive. So H is indeed a C1 diffeomorphism. In fact, it's even an orientation-preserving diffeomorphism. Okay, now if you write, if you look at the integral from x naught to f of x naught of this exponential, that's a fixed number that I call alpha, then it's easy to see, just plugging into the expression of H of x, that H composed with f of x is equal to this expression you see at the bottom. In other words, it's alpha plus the integral from f of x naught to f of x of the exponential of psi, okay? And now, if you, in this last integral, you apply a change of variables, if you write t equals f of s, okay, then you can rewrite this integral in the way it's written here in expression 2. And now you simply observe that the derivative of f calculated at s, this is the exponential of the logarithm of the f, and you can use the co-cycle, the co-boundary equation, or the co-cycle relation, I should say. Psi equals psi composed with f plus the logarithm. So you write this integrand in the way you see here in the first line of this last expression, and that's of course because you have the co-cycle relation. This reduces to alpha plus the integral from x naught to x of the exponential of psi, but that's exactly the definition of what H of x is. So in the end, what you get is this conjugacy equation. You get that H composed with f, well, it's alpha plus H, but translation by alpha in this language here is rotation by alpha, right? Because we are identifying the circle with r mod z. And so you get that if the first invariant, H1 of f, is finite, then H then F is indeed C1 conjugate to the rotation R alpha. H is C1, right? And the converse is easy, is essentially what I said before about the chain rule. So I leave it as an exercise for you. Okay, Hermann's invariant was, of course, in the late 70s, was introduced by Hermann. But before that, the problem of rigidity of diffeomorphisms was already being examined by Arnold in the analytic category. So he was studying analytic diffeomorphism of the circle, and he proved the fundamental theorem, which does not, of course, use anything about Hermann's invariant, because Hermann's invariant came much later. So I want to just give you an idea of what this theorem is all about. So he proved a theorem which states, in very vague terms, it states that every analytic circle diffeomorphism that has a good rotation number, I'll tell you what this means in a moment, and which is sufficiently close to the rotation R alpha, is actually analytic conjugate to R alpha, where alpha is the rotation number of the diffeom. So you have a result here that gives you this analytic rigidity, okay? But the map that you start with has to be close to a rotation from the beginning, okay? Now, Arnold's theorem is actually what we call like a baby version of what is now known as the KAM theorem. So there's something called KAM theory that was named after Kolmogorov, Arnold, and Moser, which essentially studies stability of Hamiltonian systems near a periodic orbit. And anyway, I'm not going to go into that, but a very special case of that in dimension 1 is the case of the one-dimensional torus, which is the case that was analyzed by Arnold. So what do I mean, first of all, what do I mean by good rotation number? Good rotation number means that the rotation number is Diophantine. And I remind you of this definition that was, I think with a slightly different notation, but it was introduced by Pablo in his first lecture, in the second part of his first lecture. So I just want to remind you that an irrational number alpha is Diophantine of type k and nu, where k and nu are certain constants, positive constants. Nu is actually greater than 2. If alpha satisfies this inequality that you see here, alpha minus p over q, so the distance between alpha and a rational p over q is always greater than or equal to this constant k divided by q to the power nu, okay? So this is saying that alpha is somewhat quantitatively distant from rationals in some sense, okay? Of course, the rationals are dense on the line, but I'm saying, you cannot approximate alpha by a rational p over q with an error smaller than this power of q, okay? Now, Pablo mentioned in the first lecture that the set of all Diophantine numbers actually has full Lebesgue measure on the real line. So since we're going to be dealing with rotation numbers, alpha will actually range only between 0 and 1. So we have a full Lebesgue measure set inside 0, 1 as well. So almost all numbers are Diophantine of some type, okay? So given this terminology, I can now give you the statement of Arnold's theorem. It's just a teeny bit technical, but it's going to tell you the following. So suppose you're given a number greater than 1 and two constants k and nu. K is positive and nu is actually greater than 2. And suppose you have a Diophantine number between 0 and 1 of type k nu, okay? Then you can find some epsilon that depends on these data. It depends on r, depends on nu, and depends on k, that having the following property. So if you have a diffeomorphism with this rotation number alpha with the following, satisfying the following conditions. So first condition is that f has a univalent extension to the annulus, A sub r, which is the annulus that has external radius r and internal radius 1 over r, okay? So what do I mean by univalent? I mean the holomorphic injective function. I'm still denoting it by the same name. So in particular, f is on the circle, f is reoanalytic, okay? So it has this holomorphic extension, so it's reoanalytic. And the second condition that has to be satisfied is that f is actually close to the rotation by alpha in this whole annulus, okay? All right, so then the conclusion is that you can find another holomorphic injective function, in fact, a univalent function, h, on a smaller annulus, a slightly smaller annulus, okay, a sub square root of r, so it's smaller than a sub r, with the property that h still preserves the unit circle. So since it's univalent, it's actually going to give you an analytic diffeomorphism of the circle, and such that h actually conjugates f to the rotation r alpha. Okay, so the conclusion of this theorem is that f is analytically conjugate to the rotation by alpha on the circle. Okay, and in fact, it's even a bit stronger. It's in an annular region around the circle. Okay, so that's the fundamental theorem of Arnold, and the proof requires controlling what we call small denominators, and I will give you an idea of what that means in a moment, okay? All right, so first of all, I should say that the way Arnold proves this theorem is actually following a kind of a general strategy that was laid down by Kolmogorov a few years earlier than that. In fact, there is even an ICM address where he does that. Kolmogorov was really more interested in the general context of Hamiltonian systems, so he proposed a strategy. I'm not going to tell you the whole, the strategy, Kolmogorov's strategy in general. I'm going to give it to you here in the specific context that we are dealing with. So, so this is really the strategy that Arnold followed in his paper. So the first step is to, you have this nonlinear equation, f composed with h is equal to h composed with r alpha. That's a very, very nonlinear equation in h, right? So you try to first linearize the equation. So you linearize the equation by writing, you're assuming that f is close to a rotation, so you write f equals to the rotation plus a small perturbation. And you're looking for an h that you also expect to be close to the identity, right? So you write h as the identity plus some small perturbation. And then you expand everything out and just look at the first order terms, and you get a linear equation. I'm going to get to that in a moment. But then you expand everything into Laurent series because you are in an annulus, right? Everything is analytic on an annulus. And you get an approximate solution. But when you do this approximate solution, you actually get that the solution is defined on an annulus which is slightly smaller than the original annulus. So you have what we call a loss of analyticity, okay? So this solution is holomorphic, univalent, preserves the unit circle because of some symmetry that you have. So, but in order to prove the convergence of the series for H1, that's why you need to shrink the annulus a little bit, and you also need to use in an essential way that the number alpha is Diophantine, that in some sense it's kind of badly approximable by rationals. Okay, so then with this, you can, H sub 1 is not an exact solution of the equation that you're looking for. It's an only approximate solution. So what you can do is you can take H sub 1 and you can take f, the original f, and you can conjugate f by this H sub 1, and you get a new f1. This f1 is, again, analytic, defined on an annulus around S1. It's holomorphic univalent, right? So it also preserves a unit circle. So it's a new diffeo. It's a new analytic diffeo, and it has the same rotation number as f. That's important, okay? So then what you can do is you can do with F1 what you did for F. And then you can keep doing this inductively. So the second step is this induction step. So you repeat this process. So you replace F1 with, you replace F with F1 and proceed inductively. So you get two sequences. You get a sequence of univalent maps which are close to the identity, these H sub n's, okay? They are defined in smaller and smaller annuli, okay? And you get a new sequence, another sequence of diffuse, all with the same rotation number as the original F. And they satisfy this relation that you see there, that F sub n plus 1 is H sub n inverse composed with Fn composed with H sub n, okay? All of these maps preserve the unit circle, but they're all defined on annuli, and these annuli are shrinking, and you don't want these annuli to shrink too much. Otherwise you lose completely the analyticity. And if you, of course, if you expand, if you write the Fn in terms of the original F, you get this equation that you see here. And now what you need to do is you need to compare the distance between F sub n and the rotation. Okay, and the interesting thing here is that the method will give you something akin to Newton's method. It will tell you that when you go from one step to the next, the F sub n plus 1 is actually definitely closer to R sub alpha than F sub n. The error that is committed is actually a power, 1 plus epsilon power of the previous error. Okay, so the errors are actually going down faster than linearly. Okay, and the estimates also show that you lose this analyticity, but you don't lose it completely. You kind of go, these R sub n's, these widths of these annuli, they shrink, but they don't shrink to 0. Okay. Anyway, this is a hard part of the proof. There's a lot of estimates involved here, and there is a kind of, in some sense, a bootstrap. And what makes the procedure work is the fact that this faster than linear decay that you have here on the second step beats the loss of analyticity that you have in the first step at each stage of the induction. Okay? So this is a general idea of what the proof looks like. Of course, this is very vague, but you will find a complete proof of the theorem, of Arnold's theorem, in chapter 4 of our book. Okay, the proof is completely written down there. Okay, but here I want to at least give you a flavor. I want to give you an idea of how step 1 is carried out. Step 1 is this step where you consider the linearized problem, right? And I want to do that in order to show to you how the small denominators creep in. Okay, so instead of working with the maps themselves, it's usually much more convenient to work with the lifts of these maps to the real line. And in these terms, the problem reduces then to, so F, capital F is the lift of small f, and capital H is the lift of the small h, which is the unknown. It's the map that you're looking for, right? So your goal now is to solve this equation, F composed with capital F composed with capital H is equal to capital H composed with capital T sub alpha, where capital T sub alpha is the translation by alpha, which is the lift of the rotation by alpha, okay? So what we do is what I mentioned before. You write F as a perturbation of the translation, and you write H as a perturbation of the identity. Okay, these maps have to be periodic of period 1 because these are lifts of diffuse of the circle. So phi of z is given, and psi of z is the unknown. Okay. So if you plug this information into equation 3 that you see there on the slide, you realize that you will have to solve this equation that you see here at the bottom, right? But this doesn't look any easier than equation number 3, In fact, if anything, it looks even a bit more complicated. It's still a very nonlinear equation, and it's very difficult to solve it directly. So what you do is you get rid of this term z plus psi of z. It's psi of z that you have there. You can expand this. You can use the Taylor's formula for psi, for phi, sorry, to write this the linear term plus higher order terms, and you ignore the higher order terms. So what you're really trying to do is to solve this linearized equation here. Okay, so phi is given, and you want psi. Okay. So once again, this is a kind of a co-boundary equation, or a co-cycle equation. And of course, there is a problem here, which is, a necessary condition for this equation to be solvable is that the integral of phi has to be 0. But, the integral was given to you, the integral of phi, phi was given to you, and there is no reason why it has to satisfy this condition. So what you really need to do is you need to change this equation a little bit. So you replace this equation 4 by this equation 5 that you see here, okay? So now you see I added this term minus phi hat of 0, where phi hat of 0 is the integral, okay, from 0 to 1 of phi. So if I subtract that constant, then now the equation makes perfect sense, okay? And you can use a Fourier series to solve this problem. So you expand phi in Fourier series, as you see in expression 6, where the coefficients are, they're given by this expression 7 that you see here, which are the usual expressions for Fourier coefficients. I remind you that these functions are z-periodic. They're periodical period 1, okay? All right, so you can also formally expand the unknown psi in Fourier series, and now you're searching for the coefficients. And if you formally put this information back into the equation, the equation number 5 here that you see here, and you solve for the coefficients, you deduce that, well, the first coefficient, psi hat of 0 is 0, and the other psi hats, psi hat of n is given by this formula that you see here, this ratio of phi hat of n divided by e to the 2 pi I n alpha minus 1 for all n integer, non-zero integer, okay? Now you see, these numbers, e to the 2 pi I n alpha, they are dense. These are complex numbers of modulus 1. They are dense on the circle. So ever so often, they're going to be very close to 1. So these denominators are going to be very small. And this is very dangerous if you want to prove convergence of the series for psi. Okay, so this is where the small denominators creep in. It's in this step. So how do you get convergence of psi? Well, you have to deal with the small denominator. So first thing you do is you use the fact that alpha is Diophantine to get this inequality here. That the denominator of these expressions that you see here, the expression 9, right? In the right-hand side of the expression 9, the denominator in absolute value can be bounded from below by this expression you see there. It's essentially a constant, 4 times k, divided by a power of n, a power greater than 1, because nu is greater than 2, okay? All right. So if you plug this, information in the equation for psi, you already see that these numbers, absolute value of n raised to the power n nu minus 1, these numbers are going to be in the numerator. They're going to go up, and they're getting big, right? Because you're letting n go to infinity on both sides. So potentially you have problems there. However, this is mollified in some sense by this second estimate. So it's a general fact that if you have a holomorphic function, okay, which is periodic or period 1, then its Fourier coefficients have a very fast decay. They have an exponential decay, and the actual formula that gives you this bound is what's written in this lemma. So if you have a holomorphic function, which is periodic of period 1 on some strip, okay, on a strip of width sigma, and you look at its nth Fourier coefficient, then in absolute value, its nth Fourier coefficient is actually decaying exponentially fast with n, with the absolute value of n, as you can see here. So there is this estimate. So this exponential decay in e to the minus 2 pi sigma times the absolute value of n, this beats this polynomial growth that you have, which is absolute value of n raised to the power nu minus 1. Okay, so with these estimates, you get convergence of the series on some strip. Okay, and now it turns out that you see here there is well, first of all, the lemma is applied for psi equal to phi, of course. Yeah, so we use this for phi, but for phi, so in order to get this estimate here, in order to have the C0 norm of psi on some strip, you actually have to narrow the strip a little bit, because the way this is proved is using Cauchy's integral formula. So you need a little bit of room to apply Cauchy's integral formula, and therefore you lose a little bit on the height of the strip where things are defined. Okay, so this is this loss of analyticity that I was mentioned to you. And okay, but once you do that, you have step 1. Okay, now I'm not going to go into any details about how you do step 2, which is really fairly difficult. But like I said, all the details of the proof are given in chapter 4 of our book. Okay, so I would like to point out that Arnold, in the same paper where he proved this theorem, he also produced examples where you have diffeomorphisms that have very bad rotation number. They're very far from being Diophantine. They're things like Liouville numbers, and which are non-linearizable. So you have diffused, arbitrarily closed rotations with bad rotation number, and they are not analytically, they're not even C1 linearizable. Okay, so I want to give you an idea, and in fact, I want to give you a proof that such examples exist. But for that, I need to do a little bit of an intermezzo and talk a bit about one-parameter families of diffeomorphisms. Okay, so given any analytic diffeomorphism, so for this part, I'm only going to look at analytic maps, right? So if you're given an analytic diffeomorphism, you can always precompose it with a rotation, with rotations, with a family of rotations, and you can generate a one-parameter family of analytic diffeos, okay, which is this family F sub alpha that you see there. So you just precompose F with R sub alpha for every alpha in R mod Z, or you can think of it as a number between 0 and 1. So this is usually, I mean, we refer to it as the standard family generated by F, okay? Or sometimes just the standard family of F. And what you can do is you can look at the rotation number, how the rotation number varies along this family. So we know already from what was said in lecture number 1 that the rotation number is actually continuous, right? So it varies continuously on this family. But moreover, it actually varies monotonically, okay? So as you increase alpha from 0 to 1, right? The rotation number increases, okay? Now, what I really mean is that the rotation number function has a function from R mod Z to R mod Z is order preserving. It's actually it's orientation preserving, if you will. Okay. It's continuous and monotone, but it's definitely not injective because, I mean, unless something very special happens with F, or okay, for most Fs, this is not going to be the case. So in fact, we have the following lemma. So suppose you have such an analytic diffeomorphism and you form the standard family associated with it, and suppose that these maps have the property that they are not periodic. Okay, they are not periodic maps. So no power of these maps is equal to the identity. Okay, there is a simple condition. In fact, it's very easy to. It's not difficult to prove that if F itself satisfies this condition, that it's aperiodic, it's not a periodic map, then all of the maps in the family will have the same property. Okay. If this condition is satisfied, then the rotation number function is actually what we call a devil's staircase. It will so more precisely, it will have the property that every time the function reaches a rational value, this rational value persists for a little while. So you have an interval of parameters for which the rotation number is equal to that rational. Okay, so and this interval, so you take the maximum interval satisfying this property. You have like a closed interval, which I call delta sub r for the rational r. This interval has always a non-empty interior. And the complement of the union of all these intervals, the interiors of these intervals, is a Cantor set. Okay? And in fact, if you forget the endpoints of these intervals, if you remove these endpoints, which are on the Cantor set, so you have a countable set of values, and in the remaining of k sub f of this Cantor set, the function theta sub f increases strictly. It's strictly increasing. Okay. So these intervals, they get a special name. Okay. So when you fix a rational r and you look at the set of all parameters in the family, for which the rotation number of the corresponding map is equal to r, this interval is called a phase locking or mode locking interval. Okay. So this is this devil's staircase phenomenon is what usually people call a mode locking phenomenon. Okay. Okay. So what is an example? The most famous example of a family of this type is actually, or various families of this type, is coming from a two-parameter family, which is called the Arnold family. So you start with this family of entire maps of the complex plane. So f sub alpha beta of z or z is equal to z plus alpha plus beta times sine of 2 pi z. Okay. And so these are entire maps. And they satisfy this condition that f sub alpha beta of z plus 1 is equal to f of z plus 1. Okay. So they can actually be quotient down to maps of the cylinder of C mod z, which is really the punctured complex plane, okay, whose restrictions to the unit circle are actually analytic diffeomorphisms, okay. Of course, for this for them to be diffeomorphisms, beta has to be in this range that you see there. Beta has to be between 0 and 1 over 2 pi. This is a simple calculation. You know, just calculate the derivative of this, and you see that on the unit circle, if beta is between 0 and 1 over 2 pi, on the unit circle, on the real line, the derivative of these maps is always going to be positive. Okay. All right. So these f's, they quotient down to holomorphic self maps of the cylinder, and the restriction to the unit circle is the restrictions are analytic diffeomorphisms. Okay. Because you see, if you look at capital F sub alpha beta, it's really the composition of f of 0 beta you compose on the left by the translation by alpha. So when you take the quotient on the cylinder, you get that these f alpha sub betas, they are r sub alpha composed with f 0 beta. So So if you fix beta and vary alpha, you get this one of these standard one-parameter families, and they satisfy the hypothesis of the lemma. These maps are not periodic maps. No power of them is equal to the identity. This is very easy to see, because if this happened, then for this family of entire maps that you see here at the top, you would also have the same property that they would have to be equal to what, a power of capital F would have to be a translation, okay? But then in particular, this would mean that these Fs would be invertible, but they are entire, and they, if they are entire maps, they're defined in the whole complex plane, they're analytic, and they are invertible, then they must be affine. And therefore, it's easy to see, because they preserve the real axis, that they actually have to be translations, okay? And this is not the case. So these maps do satisfy the hypothesis of the lemma. So you see that for each beta that you fix, you have a Devil's staircase. The rotation number function for this family F sub alpha beta with beta fixed is a Devil's staircase, okay? So in fact, you can see this in this following picture. So here I have plotted the Devil's staircase is corresponding to two different values of beta in this Arnold family, okay? On the left, you see beta equal to 0.125. And on the right, you see beta equal to 0.158, which is very close already to being 1 over 2 pi. So this is getting close to you see, when one thing I should say is that when you get to beta equal to 1 over 2 pi, these maps are still homeomorphisms of the circle, but they are no longer diffeomorphisms. There is a critical point appearing. The critical point appears at z equals to 1/2, okay? So so these maps that you get there, they're what we call critical circle maps, and they will be the subject of the next 3 lectures, okay? So these maps are maps which are at the boundary of chaos, as we usually call, okay? If you go beyond, if you take beta greater than 1 over 2 pi, then you get an endomorphism of the circle. This map is no longer invertible, and then potentially things like horseshoes and things like that appear, and therefore you have like positive topological entropy, unlike zero topological entropy, which is the case for these maps. So for these reasons, we usually say that these maps for beta equal to 1 over 2 pi, they are at the boundary of chaos, okay? But we're not going to go into that. So you have this Devil's staircase picture, and you can see that the Devil's staircase, the plateaus, the places where the graph is horizontal, they're becoming thicker as you increase the parameter beta. Okay, so on the left you see you have a smaller value of beta than you have on the right, and you can clearly see that the plateaus that you have for the green map here, they're bigger than the corresponding plateaus for the red map here. Okay, and unlike the picture might suggest, because of thickness of lines and stuff like that, there's no smoothness there whatsoever. I mean, there are plateaus everywhere. Okay. All right, so this is the comment I made before, is that when you get to beta equal to 1 over 2 pi, you have a critical point. So these maps are called critical circle maps. When beta goes beyond 1 over 2 pi, the maps are no longer invertible, and we're not going to talk about them in this course. And of course, for each fixed beta, you can consider the Cantor set that we defined previously. And it's a theorem proved by Hermann in 1979 that these Cantor sets have positive Lebesgue measure when beta is less than 1 over 2 pi. When beta is equal to 1 over 2 pi, you still have a Devil's staircase, and still makes sense to look at the Cantor set, which is the complement of the union of the interiors of these phase mode locking intervals. But it turns out that this Cantor set now has a 0 Lebesgue measure, and in fact has Hausdorff dimension strictly less than 1. This was proved by Grzegorz-Świątek in 1988. Okay, I mean, not the part on Hausdorff dimension, but the part on 0 Lebesgue measure. The part of Hausdorff dimension was later. It was a later work with in collaboration with Jacek Grajcik. Okay. Now, if you look at, there is an interesting picture you can draw, which is, I want to show you this slide because it took me a while to actually, I wrote a Python code to generate the picture that you'll see in the next slide. And on my desktop, it took 2 hours for the picture to be drawn. So what is this picture? You can look in parameter space, the whole Arnold family on the rectangle, right? I mean, parameter alpha varies between 0 and 1, and beta varies between 0 and 1 over 2 pi. So on this rectangle, you can look at the parameters for which you have rational rotation numbers, okay? So if you fix a rotation number, and you look at all pairs of parameters for which the corresponding map in the Arnold family has rotation number p over q, then what you get is a connected set. And this connected set is called an Arnold tongue because the shape of these remembers some kind of a tongue, okay? So here's the picture. And like I said, you know, the picture is not going to be so nice because, well, you can see it here. Each one of these black regions that you see here is a tongue, okay? And it's a tongue corresponding to the rational number that you see at the bottom, okay? You see, when beta is equal to 0, this family is just the rotations by alpha, right? So when you set beta equal to 0, you get the family of rotations. So you have all these rationals between 0 and 1. They're from this dense set. So I'm looking at some of these rationals. I'm looking at these rationals that you see there. There's like 9 values of the rational p over q there. And for each one of them, the program has drawn the corresponding Arnold tongue. So as you increase the parameter beta from 0 to 1 over 2 pi, you see there's a normalization here. The y-axis here is actually pi times beta, okay? So that's why it goes up to 1/2 there. But anyway, when you increase beta from 0 to 1 over 2 pi, these tongues, they open up, okay? So if you fix a beta, so this is like fixing a horizontal line. So if you fix this horizontal line and you intersect it with these tongues, there are tongues everywhere, not just the ones I've drawn here. You get the gaps of the Cantor set, the complement of the Cantor set, okay? And the Cantor set has positive measure for beta less than 1 over 2 pi, but when you get to the top, see the gaps are kind of becoming thicker. So it's kind of reasonable to expect that the measure is going down, and in fact, it gets to 0 when you get to beta equal to 1 over 2 pi, okay? So that's the picture. Like I said, it took 2 hours for this thing to run, and I'm still not entirely happy because, as you can see, these lines that appear here, they should be smooth lines, actually, okay? But they appear a little jagged at the bottom, as you can see. At the places where they're really narrow, they appear a little jagged, okay? Anyway, so that's the intermezzo about one-parameter families. So now we can talk about counterexamples to the linearizability, okay? So these are the counterexamples that were devised by Arnold in his paper. So this will actually, the way we are going to do it is not the way Arnold did in his paper. We are actually going to give a proof of existence of these examples without explicitly exhibiting these examples, okay? In Arnold's paper, there is a more sophisticated approximation argument, which you'll find in the book as well. The whole thing is in the book, in chapter 4 of our book. And here we are only going to give the existence of such examples, okay, by using a bare category argument. So examples of what? So these are examples of analytic diffeomorphisms, which have irrational rotation number, but are not even C1 conjugate to the corresponding rotation. Okay, we know that they are topologically conjugate because of Danjois' theorem, but they are not even C1 conjugate to rotation. And the reason why this happens is because the irrational rotation number is actually very bad, okay? It's very fastly approximated by rationals. So, okay, so, and to do that, so like I said, it's an indirect argument using a bare category, the bare category theorem. And we will also have an opportunity to use Hermann's C1 conjugacy invariant. And this is the reason why I spent some time on it. So, so let's look at, given an analytic diffeomorphism satisfying the hypothesis of the lemma, in other words, no power of it is equal to the identity, okay? So you consider the standard family associated with it. So you precompose with the rotations R alpha, let alpha vary. Look at the Cantor set that was defined earlier, okay, as the complement of the union of the interiors of the mode locking intervals. The theorem states then that there exists a residual set of parameters inside this Cantor set, such that for every parameter in this residual set, the analytic diffeomorphism F sub alpha is not C1 conjugate to the corresponding rotation, the rotation with the same rotation number, okay? So there are plenty of non-linearizable maps. And also, by taking F already very close to a rotation, okay, analytic and very close to a rotation, all of these maps will be close to rotations, okay? So you're really violating the conclusion of Arnold's theorem, okay? So the proof is quite simple if you use the Hermann invariant. So first of all, there are all these mode locking intervals, and these intervals have endpoints which lie on the Cantor set K sub F. So let me denote by D sub F the set of all such endpoints, okay? So these are endpoints of phase locking intervals. So observe that at these points, the rotation number function of the family is rational, assumes a rational value, okay? So these points, this is a countable dense set of points inside the Cantor set, okay? Okay, and like I said, for each alpha for each parameter in this dense set of points, the corresponding diffeomorphism has a rational rotation number, but it cannot be C1 conjugate to the rotation R P over Q, because in that case you would have to have F alpha to the Qth power of F alpha equal to the identity, and this violates the hypothesis we made on F, okay? So you cannot have that. So these maps are not C1 conjugate to the rotation. So therefore, by Hermann's criterion, the Hermann invariant calculated that these guys has to be infinite. Okay, so there is this countable dense of set of points, dense in the Cantor set K sub F. And at each one of these points, the Hermann invariant is infinite, okay? So now let me define a bunch of open sets. So I for each K, positive integer K, I denote by V sub K the set of parameters inside the Cantor set, K sub F, that have the property that Hermann invariant of these guys, calculated at F of these guys, is greater than K, okay? Then just because of the definition of the Hermann invariant, right? This is an open condition, so the VKs, the V sub Ks are open sets, okay? And of course, D sub F is contained in V sub K for every K, right? Because at points in D sub F, the invariant is infinite, so it's greater than K, right? So VK is open, and it's also a dense subset of K sub F. But, now K sub F is a compact subset of a complete metric space, so it is itself complete. So you can apply a Bayes' theorem to it, and so you have a countable set of open and dense sets you take their intersection. The intersection is residual in the Cantor set. In particular, it's uncountable. So there are uncountably many points inside K sub f, which are in this V sub infinity. But this V sub infinity, you know, every point in this V sub infinity, it has to be in V sub k for every k. So the Harman invariant calculated of those guys at the maps corresponding to these parameters has to be equal to infinity. So again, using the Harman criterion, these diffeos cannot be C1 linearizable. So you have proven the existence of, you know, lots and lots of non-linearizable diffeomorphisms, analytic diffeomorphisms of the circle, arbitrarily close to rotations, if you will. Okay, this still leaves open the question, you know, Arnold's theorem was proven by, Arnold proved his theorem using the hypothesis that the rotation number was Diophantine. Is this hypothesis really necessary? Can we weaken it a little bit? Is there a larger class of rotation numbers for which Arnold's theorem holds? And what is the largest class for which it holds? This question turns out to be a difficult one, and it was answered by Yokos, okay? Originally, the main ideas go back to 1989, but, you know, he later rewrote these things and wrote better versions of it. So that's why you see these two dates here. And in order to state Yoko's result, I have to give you a definition, which was actually given by, I believe it was given by Pablo in the first lecture, in the second half of his first lecture. And it's the definition of a Bruno number. So we say that an irrational number is Bruno if, when you expand it in continued fractions and you truncate the continued fractions and look at the convergence of the continued fraction expansion of this number, so you have the denominators they call Qn. So if you add the series log of Qn plus 1 divided by Qn, the series converges. So if this happens, then you say that the number is Bruno, okay? So it's not, it's an exercise to show that every Diophantine number actually is also Bruno, okay? But remarkably, there are some numbers which are even Liouville, which are Bruno as well, okay? So anyways, this is a strictly larger class than the class of Diophantine numbers, okay? All right, so Yoko's theorem can be stated as follows. Well, first, some notation. I'm going to write diff omega sub b of S1 for the class of all real analytic circle diffeomorphisms that have a holomorphic extension to a map defined in the annulus A sub b, which is the set of all z's that whose absolute value is between b and 1 over b, okay? So then the theorem states that if you have any Bruno number and you take any b greater than 1, okay, there exists an epsilon that depends on these two data with the following property. If you have a diffeomorphism which is of this type, is in this class, right? So repeating, it's defined on the annulus. F has a holomorphic extension to the annulus A sub b, okay, and has rotation number rho, and it's close to the rotation by rho by less than epsilon. So the distance between F and R sub rho is less than epsilon. If you have that, then any topological conjugacy that you take between F and R sub rho is also analytic. It's a diffeomorphism in a smaller annulus. Okay. Okay. So that's one result. So this is like Arnold's theorem, but instead of assuming Diophantine, you assume Bruno. So it's proving Arnold's theorem for a larger class of rotation numbers. But then Yokos went further and showed that this condition is actually sharp. Okay, so he showed that if you take an irrational rotation number which is not in the Bruno class, is not Bruno, okay, then you can find counterexamples. in any annulus and for every epsilon, you can find an analytic diffeomorphism which is defined on that annulus, okay? And which is epsilon close to the rotation, R sub rho, and yet F is not analytically linearizable, okay? In fact, Yokos found examples of this type which are even Blaschke products, okay? There are restrictions of Blaschke products to the unit circle. I'm not going to go into any of that. For more information, you can look again at chapter 4 of our book. And now I want to give you the statements, some statements of global results, because when Arnold proves this theorem, in the same paper, he actually raises the question, you know, is it necessary to assume that the map is close to a rotation, okay? And in the 60s and 70s and 80s and so on, people investigated this question very thoroughly, and by people I mean really mostly Herman and Yokos. So the goal was now to remove this hypothesis. Okay. Now I'll state some results first for smooth maps. So at the same time that I should tell the story a little bit better, right? I mean, Arnold proved his theorem in the analytic category. Okay. Now the KAM theorem was later proved in the smooth category. Okay, for C infinity or CK maps. Okay. So so there is an analog of Arnold's local conjugacy theorem for smooth maps, and the question also arose that, you know, can we get a global theorem? Can we get rid of this hypothesis that the map has to be close to a rotation? Okay, so this was, like I said, investigated by Herman and later by Yokos. And for smooth maps, the results can be stated as follows. So if you have a CR diffeomorphism of the circle and R is at least 3, it turns out that you need to use tools like the Schwarzian derivative. So if R is at least 3, and if you know that it's Diophantine of some exponent, so this delta now is, so this is written in a slightly different language, right? So now what I mean is that, what do I mean by Diophantine of order alpha, delta now? I mean that alpha minus P over Q in absolute value has to be greater than or equal to a constant divided by Q to the power 2 plus delta, okay? So instead of having that nu that I wrote before in Arnold's theorem, I'm replacing nu by 2 plus delta, so I'm looking at delta, okay? So if you have a CR diffeomorphism whose rotation number is Diophantine of order delta, then it will be smoothly conjugate to the corresponding rigid rotation, where smoothly means the following. As long as you take R greater than 2 delta plus 1, okay, F will be CR minus 1 minus delta minus epsilon conjugate to the corresponding rotation for every epsilon, okay? So I'm not talking about, you know, all the details. In particular, I'm not defining these differentiability classes here very, you know, I'm talking about them as if these were integers, but they're not integers, okay? So what does it mean, you know, to say CR when R is not an integer? It means that it's CK, where K is the integral part of R, and for the higher derivative you have, for the highest derivative, for the kth derivative, you have a Holder condition of exponent equal to the fractional part of R, okay? Okay, so anyway, what this theorem is saying is that if you have a CR diffeomorphism and it has a very good rotation number, then the conjugacy to the rotation will be a little bit, you lose a little bit more than 1 degree of differentiability, okay? But the conjugacy will still be differentiable. So if R is large, then the conjugacy will also be very, very smooth, okay? And again, I stress the fact that this is a global result. There's no assumption here on F being close to a rotation, Okay, so this is really a global result. It was stated like this, but it was really, the story is that, first Hermann proved this linearization result for Lebesgue almost every rotation number without really telling the class. And Yocos was the one who actually showed that this theorem is valid for every Diophantine number, okay? But that's not the end of the story. The Hermann and Yocos theorem was actually later sharpened by Katznelson and Ornstein. They proved this result here, that if you have a diffeo with rotation number rho, which is Diophantine of order delta, then any topological conjugacy between F and the rigid rotation is CR minus 1 minus delta minus epsilon, provided R is greater than delta plus 2. So you compare this to the previous theorem, you see that there was this condition that R has to be greater than 2 times delta plus 1. And this is now somewhat reduced to R greater than delta plus 2, okay? And you also, as you can see here, the degree of smoothness of the conjugacy is the same, is R minus 1 minus delta minus epsilon, okay? But now R, R has to be just slightly better than 2. It's 2 plus delta, where delta is this order of rho, okay, of the Diophantineness of rho, okay? You see, there's the main difference is that you no longer need to assume that R is greater than or equal to 3. So this proof does not use the Schwarzian, okay? All right, so, and there's this comment here at the bottom saying what it means for a map to be CR when R is not an integer, okay? Anyway, then another more recent development is that Hanning and Teplinsky, they were able to prove a version of this result which doesn't need any epsilon there. So the result can be stated as follows. So if you have a C2 plus alpha diffeomorphism of the circle, okay, so it's C2 plus alpha only. Alpha is less than 1 here, okay? So you only need this much smoothness, C2 plus alpha. And its rotation number is Diophantine of order delta. Then any topological conjugacy between F and the rigid rotation of angle given by this Diophantine number is C1 plus alpha minus delta, as long as this delta is less than alpha, okay? So this is a very nice theorem. We don't put the proofs of these theorems in the book, unfortunately, because of lack of time and space, okay? But we provide the references for you. And finally, I should say that, I should go back to the analytic case, and I should remark that Yocos was also able to find the sharp class for which the global theorem holds in the analytic category. Okay, so the global version of Arnold's theorem in the analytic category. And it turns out that the best set of rotation numbers that you have there is no longer the Bruno numbers. The Bruno numbers are good for when the map is close to a rotation. If you're far from a rotation, you can only guarantee that you have an analytic conjugacy if your rotation number lives in a class which is strictly smaller than Bruno. It's larger than Diophantine, but smaller than Bruno, okay? So his theorem can be stated as follows. Any real analytic diffeomorphism with irrational rotation number in this particular class, so this class is a class that I'm not defining here, but it sits, because the definition is a bit technical, but the class stays strictly between Diophantine and Bruno, okay? So any real analytic diffeomorphism with irrational rotation number in this class is real analytically conjugate to the rigid rotation, okay? And he also showed that the result was sharp by building counterexamples if the rotation number is not in this class, okay? So this gives you essentially a complete theory for the smooth rigidity of circle diffeomorphisms. And basically, that's all I wanted to tell you in this lecture. So thank you, and stay tuned for lecture number 3. Okay.